thanks for having me. It's always enjoyed coming back here. This is really an awesome place, and I always like talking to people from the aerospace industry. By the way, can you hear me okay? Okay, all right, great. So yeah, I think when I came here 4 years ago, that was I think that was like right before we actually reached orbit, maybe just several months before we reached orbit. So just to put things in perspective, while recent years have been good, that has not always been the case. And the first 3 flights of Falcon 1 actually failed. Well, the first flight failed quite soon. The engine shut off about 30 seconds into flight and continued ballistically for another 30 seconds, and then landed like an anti-tank weapon not far from the launch site. At some point, we'll release the blooper reel, but I think we'll wait a few years before we do that. Yeah, but from those first days, where myself and the rest of the team were picking up bits of rocket off the reef, things have come a long way, thank goodness. So we actually had 2 more failures after that one. Then the 4th flight in late 2008 was successful, and that was a close one because I'd run out of money, and there weren't a lot of people that were keen on funding a rocket company. And I think if we'd said yes, our 4th launch wasn't successful, but the 5th one's the charm, that would not have gone down well. So it was. Thankfully, the 4th launch did work, and that I think gave customers, valves, NASA, and others enough confidence to award us additional launch contracts and for private investment, additional private investment to come in and help fund the company besides myself. Yeah, I'd like to certainly thank those investors, Draper Fisher-Jurvetson and Founders Fund and Battle Equity, for having faith there at that early stage to invest in a rocket company. So since then we got that 4th launch demonstration launch to work, and then we did our first satellite launch, which was a commercial mission for Malaysia, and that launched Razak-SAT into orbit, and I think it's actually still up there. And then we were able to go from there to develop the Falcon 9. And the Falcon 9, we leveraged the engine we developed with Falcon 1, the Rolling 1C, and essentially ganged 9 of those together on the first stage, and then 1 on the upper stage with an expanded nozzle. And that actually gave us about 20 times the payload capability of Falcon 1. Because in the case of Falcon 9, we were using a pump-fed upper stage as opposed to a pressure-fed upper stage. It's an important difference for those of you familiar with how rockets are designed. It seems we learned most. We took most of the lessons learned from Falcon 1 and were able to apply that to Falcon 9, so that the launches of Falcon 9 were all successful. They all reached orbit. Sometimes there was a little glitch along the way, but they all reached orbit. And there's an advantage to having the 9 engines, because if one of them doesn't work and has what we call a RUD, which is a rapid unscheduled disassembly, then it still makes it to orbit. And that's important. I think it's a good principle to have. It's something we think is important for commercial airliners. That's why all commercial airliners have multiple engines, so that if you're going across the Pacific at night and you lose an engine, you don't kind of have to use that life raft or that jacket that they give you, which I think has not been used effectively very often. So the multi-engine I think is good, and we're going to keep that philosophy going forward. And where we're going now is to the next generation of Falcon 9, which is a vertical takeoff and landing capability. And I'll show you the video, which is the first sort of flight of the Grasshopper project. That's it. Right, the connection's working particularly well, but well, if you're on So that craft is actually quite big. It's about 10 stories tall, and it's that flight was to about 5 meters. And in the coming months, we'll be increasing the envelope, just doing the sort of thing that you do with the aircraft, where you have envelope expansion. You gradually increase the altitude and speed, and as you see things getting a little wobbly, then you take corrective action, ideally before before there's a crater, and you can iterate to a successful outcome. I do think there probably will be a few craters along the way, so I mean, make sure that I do think that's the likely outcome. We'll get very, very lucky if there's no craters along the way of creating a vertical landing rocket. Obviously, we know how to do vertical takeoff, but we need to do vertical landing. And the reason to be able to do the vertical landing is we're aspiring to achieve a breakthrough that I think is extremely important for rocketry, which is rapid and complete reusability. And it's important that it be both rapid and complete, like an aircraft, or like a car, or a horse, or a bicycle. Even if you had to repaint a plane between flights, you would probably more than double the cost of the ticket. So it's really, you really got to be able to just reload propellant and fly again. And that's going to take a bit of effort. So it's not going to happen overnight, but we want to keep going in that direction until ultimately it's as close to aircraft-like dispatch capability as one can achieve. And if you compare the cost of the rocket to the cost of the propellant, you can see why. Because the cost of the propellant is only about 0.3% of the cost of the rocket. And we have a low-cost rocket, so sometimes our rocket is expensive. The Falcon 9 is $60 million. And that's for something with 4 times the thrust of the 747 and about the same liftoff mass. So that's a good deal. The propellant is only $200,000. And so if we could use let's hypothetically use the Falcon 9 rocket 1,000 times, then the capital cost would go from being $60 million a flight to $60,000 a flight. Obviously, that's a humongous difference. Now there would be some incremental costs in terms of servicing, just like you have on the aircraft, or you've got to have inspections and servicing and do all that sort of thing. So there'd be that cost to take into account, but still, it would be dramatically more cost-effective to fly, to get to orbit. And I think it would open up opportunities today that are hard to appreciate. Just as in the early days when they were just doing the early days of aviation, I was just in the Camel room and looking at the Sopwith Camel. I don't think people could have envisioned that you'd be able to take a 747 non-stop from Los Angeles to London. So it's difficult for us to say, oh, we can see today where things will be in the future. But if we enable that capability and dramatically improve the technology, then I think we'll see all sorts of things happen. But we've got to make that happen. We've got to achieve that goal. And I think it's a pivotal step on the way to establishing establishing a self-sustaining civilization on Mars. If we don't do that, I just don't think we'll be able to afford it, because it's the difference between something costing, 0.5% of GDP and all of GDP. Obviously it can't be all of GDP. We get a lot of complaints about that. and 0.5% of GDP, or maybe 0.25% of GDP. Okay, that's manageable. And I think most people would agree that even if they don't intend to go themselves, that, let's say, spending somewhere between 0.25% and 0.5% of GDP on establishing a self-sustaining civilization on another planet is probably worth doing. Sort of life insurance for life collectively, and that seems like a reasonable insurance premium. And plus, it will be a fun adventure to watch, even if you don't participate. Just as when people went to the moon, only a few people actually went to the moon, but in a sense, we all went there vicariously. I think most people would say, well, that was a good thing. That was. If people look back in the 20th century and say, what are the great things that occurred in the 20th century, that would have to be right near the top of the list. So I think there's value even if someone doesn't go themselves to have such a thing. So that's why it's really important. And then if you get to, well, why don't we have fully and rapidly reusable rockets? Why doesn't someone just do it? It's quite tricky. That's the reason. So we live on a planet where this is not easy. It's possible, but quite difficult. If we lived on Mars, this would actually be quite an easy thing, relatively speaking. But at 1G, this is a just barely possible thing. And the reason it hasn't occurred in the past is because when people have tried to design a rocket, and even one that's expendable, then after a lot of smart people have worked on the rocket and done, using advanced materials and analytical techniques, you typically get 2 to 3% of liftoff mass to orbit. And that's expendable. And now you say, okay, well, what if you want to add in the reusable bits? Adding in the reusability turns out takes another 2 to 3%. So then you end up with 0 or negative. There's not much point in just sending a rocket to orbit with nothing on it. And so in the past, things have been cancelled when it looked like success was not one of the possible outcomes. In fact, usually they were cancelled after it was clear that success was. So a few years after it was clear that success was not one of the possible outcomes. So the trick then is to make a rocket that's so mass efficient that it gets close to 4% of its payload to orbit in an expendable configuration, and then improve the weight of the reusability bits, push that down to around 2%, so you get a net of 4 minus 2. So you're on the order of 2% of your payload to orbit in a fully reusable scenario. And that requires being paying incredibly close attention to every aspect of the rocket's design. The weight of obviously the efficiency of the engine, the weight of the engine, the weight of the tanks, the legs, even the secondary structure, just the wiring and the plumbing and the electronics, making sure your guidance system is extremely precise, and pulling all sorts of tricks, every trick in the book, and then coming up with some new ones, in order to achieve that level of mass efficiency. Now, I think I see a path to making this happen, but those could be famous last words. And so that's what we're seeing the beginnings of, and it'll take a while, and I'm not sure how long it'll take, but I'm hopeful that we can start to bring back the first stage in the next year or two. We've already brought back Dragon, so we know what bringing something back from orbit is like. And we can start to reduce the mass required to come back from orbit, because you really have to hone it down so that the thermal shielding and the strengthening of the structure is only just what is needed to come back, and not anymore. And then I think perhaps full reusability is in the 5 or 6 year time frame. could be famous last words. So that's our goal. That's the most important thing, technically, that SpaceX needs to achieve. And in parallel, we're doing things like the Falcon Heavy, which will have two additional side boosters, two additional first stages of side boosters. And with the upgraded thrust of Falcon 9, that will take it to about maybe 60% to 65% of the thrust of a Saturn V, just to put it into perspective. So maybe around the 4.5 million pound thrust level, which is about twice as powerful as any other rocket on Earth. But I think obviously if you want to go to Mars, you need something even substantially bigger than that. So some future vehicle, I think, would probably aim to be quite a bit bigger than that. Yeah, so that's sort of where SpaceX is, and I think sort of stay tuned for more developments. But with that said, I'm happy to answer any questions from the audience, and yeah, so let's just jump in.
We have volunteers who are going to bring microphones, so can I ask that anyone who asks a question gives their name and affiliation before asking the question. In addition to people in the room asking questions, the Society has also been putting out on Twitter the ability to ask questions, and I have several on this sheet, so I will at some point ask some of these questions. But I think first of all we'll start with questions from the floor here.
Will you be able to cover this side, Pat?
Actually, I should have remembered to play this video. This gives you a sense of what I'm talking about for the reusability. Now, this was done by sort of a modeling team. It wasn't done by the SpaceX engineering team, so it's not entirely physically accurate, but it gives you a sense for things at least. So now we've gone through stage separation. So the first stage is going to turn around and reignite. It's actually going to reignite 3 of the engines, not, yeah, okay, so showing 3 there. But it sort of magically got rid of the interstage, which obviously is not really. And the real legs are much bigger than that. Those are little guys. But that's approximately, imagine much bigger legs and a much taller stage with an interstage on top, and it's approximately what it would look like. Yeah, so that's the vehicle, and then there's the next generation of Dragon, or Dragon version 2, which this actually does not look like that. But we'll be unveiling that fairly soon. Yeah, I think it looks pretty cool. But Dragon version 1, we didn't really know what we were doing. We know slightly more at this point. So that's why Dragon version 1 looks sort of similar to things that have occurred in the past, because we thought, well, we better not stray too far from things in the past, and hopefully it works. So it was lost. so the next version of Dragon will do that, but it looks a bit different. But it'll have legs that pop out, and it has eight thrusters that are arranged in 4 pairs around the exterior. Now the actual vehicle, the pairs are not quite at 90 degrees apart, because we wanted to shift the engines that are on the windward side of the back shell a little more towards the leeward side. So they're not quite at 90 degrees apart. They're a little sort of closer together on the sides. And they're much bigger than what you see there. Because the Super Draco engines are designed to accelerate the Dragon spacecraft at over 6 Gs. So you can go basically, depending upon what sort of dynamic pressure you're facing, go through the sound barrier in about 3 seconds.
Even faster than your Tesla.
Yeah, actually, yeah. Because if you're at altitude, your thrust increases, so you're actually more like at 7 to 8 Gs. Yeah, so it's 4 seconds.
You can hear me now. So I'm Rob Coppinger with Space.com. Thanks for your talk. So you've been quoted in the past as saying a private Mars colony, somebody could go for $500,000. Is that based on a detailed study? Have you carried out a detailed study of what it would take to get people there and the mining equipment, how they become self-sufficient? And also, will Dragon Lab be Dragon version 2?
Sorry, you're asking what have we done with respect to thinking about Mars sort of colonial systems?
Yeah, have you done like a real any sort of detailed study to be able to come up with the $500,000 price tag?
Oh, yes. So the question is sort of how did I come up with a $500,000 price tag to move to Mars? I sort of started back from the $500,000 point to sort of say, okay, well, in order for Mars to become a self-sustaining civilization, the ticket price has to be low enough that if someone were to work hard and save up, then most people in advanced countries, after let's say in their mid-40s or something like that, could put together enough money to make the trip. So I thought, okay, $500,000 will, that's like a middle-class house in California, basically. It's kind of sometimes hard to get one for $500,000. So something on that order. That's about the right order of magnitude. And then working backwards, well, you definitely need to have full reusability, because even partial expendability would kill that price. And then you need to use a source propellant, for a source fuel, I should say, because liquid oxygen is incredibly cheap. Liquid oxygen is like 2 to 3% a pound. So really it comes down to the fuel and the pressurant. And well, the cheapest fuel is methane. So it's going to be methane. And also the nice thing about methane is that you can create it on Mars. Because Mars has a CO2 atmosphere, and there's a lot of water ice in the soil. And conceivably, you might be able to extract water vapor from the atmosphere, but that may be harder than simply mining water. But then with water, you've got H2O, with plus CO2, that gives you CH4 plus O2, and bingo, you can replenish propellant. And you can do this either with hydrogen or with methane. And for a while, we were sort of going down the hydrogen path, and then I was looking at the numbers, and you get to roughly equivalent delta V with methane or hydrogen because of the better mass fraction of the methane system. And then you combine that with the much easier, the fact that methane is much easier to deal with. It's not a hypercryogen, and it doesn't have that sort of wiggly hydrogen molecule that likes to get into all sorts of unpleasant places. And it does sort of like metal embrittlement and create sort of invisible high temperature fires and that kind of thing. So methane is just sort of a much easier thing to deal with. And So the performance is about the same, easier to deal with, obvious move in retrospect. And actually with the properly designed methane engine, it's a staged combustion engine, then you can achieve with decent combustion efficiency in the 99% range and a reasonable sort of area ratio. 380 ISP is quite achievable. In fact, the Russians in ground tests have achieved 380 ISP. So this is clearly an achievable number. So that's sort of the direction we're thinking of going for that. So yeah, and then you want something that's pretty big, because if you're going to go spend a lot of months in it, it can't be the size of a minivan. A round trip to Mars with 6 months there, 18 months on the surface, 6 months back, 2.5 years. You want a little room. I would shudder to think of doing that in Dragon. You'll come back batty, if you come back. So I think Dragon could be quite useful as a generalized science delivery platform for anywhere in the solar system, because with propulsive landing, you could that's a generalized solution. So you could land on any solid or liquid surface in the solar system, and I think really enable a lot more science missions for a given budget if getting there is taken care of. So that's why I do think Dragon is going to be sort of useful in that respect. Apart from being able to carry cargo and people to Earth orbit missions and maybe some other missions too. Yeah. Thanks, man.
Andrew Rackett there, Ashton. So, in your design, you're saying there's from my perspective, there's two ways of designing the booster. There's the gun booster, the big gun booster that's designed for cost, and it's low cost. And then there's the other way that you check performance, which is the path that NASA has fallen down quite a few times.
I think it's a false dichotomy, but yeah.
But with your booster,
a big smart booster.
How close is it to 2%? How close is it? And is there any other aspects you're trying to drive down costs within the operations, such as space-based ranging and that sort of low-cost approaches?
Well, a big down booster usually refers to a pressure-fed stage. It usually means minus the turbo pump. I think that's actually not a good way to go. Turbo pump, you want the turbo pump, otherwise your rocket is just too heavy. And you also, because if you go with the pressure-fed stage, you have your entire stage has to operate at something north of the chamber pressure, and then you're going to have a ton of pressure gas left there at the end of the flight. So it's just not a great way to go. And turbo pumps are hot, but they're not that hot, really. It's just a spinning centrifugal pump. It's tricky, but it's not that tricky. The hard thing about a rocket engine is just getting those last incremental seconds of ISP. That's where that's where it's really quite difficult. And those last seconds of ISP matter a lot for something that's going to go beyond Earth orbit, where every just incremental tiny bit of ISP is important. So I really think you need to push everything to the limit in terms of advanced materials, smart design of everything, high efficiency engines. It's all got to be pushed to the limit. What you don't want to do though is have insufficient margin in your engines or structure such that you have to rebuild them after returning. And that's I think an error that was made with the shuttle. Say that the SSMEs were just really difficult to reuse. And they required a lot of inspection and partial placement in between flights. So I think you need to back off a little bit on chamber pressure. Still aim for a high combustion efficiency, but back off a little bit on chamber pressure.
How close are the current SpaceX components to this goal of high performance? Do you have to do a lot of delta qualification or a lot of components to change and modify them to get this, or was it from the very beginning were the components designed to
Well, where SpaceX I think does quite well is in the mass ratio of the stages. So very good stage mass ratio. That's with the current version of Falcon 9, where the first stage is around the 94%, a little above 94% propellant by mass, and with the new design of Falcon 9, we're closer to 96, maybe 95.5% propellant. And with the slight improvement in ISP. But the Merlin architecture is an open cycle architecture, so it doesn't have the ISP advantage of a stage combustion system, and it's using RP1. So we're talking ISP for the boost stage, vacuum ISP for the boost stage engine. That's maybe around 310 to 312. And for the vacuum version, that's around maybe 340 to 345. The penalty for an open cycle engine is much less in vacuum than it is on the XC level. So that's where we are. So we definitely need a new engine for any kind of sending people to Mars kind of stuff. But I think we can still get to full reusability with the current engine, despite having a bit of an ISP disadvantage relative to, say, the Russian kerosene station combustion engines. Yeah.
Hi, I'm Vishal Mendota, UCL. Just wanted to ask, you said that Falcon 9's got a maximum acceleration of 6 or 7 G. Once it becomes
Dragon.
Dragon, sorry. Is that human certified 6, 7 G, or would you have to change the acceleration profile when you put people on it?
Actually, to be clear, when going through Escape, the Dragon, Super Draco engines on Dragon will generate a minimum of 6 Gs, and depending upon the scenario, actually that could go up to 8 Gs. Kind of depends on how much you got, how much weight you have loaded on, and whether you're at altitude or not. The rocket actually limits the thrust to 5 Gs on ascent. So in a normal, we'll actually throttle down or shut down engines in a normal scenario to limit the acceleration to no greater than 5 Gs. And that's set really by the comfort level of the satellites. The 5 Gs is that's like a nice amusement park ride. It's not too bad.
Hi, Elon. Sorry, Guy Harris, Space Tech. I've seen on your launch manifest that you have a mission slated 2015 Bigelow Aerospace. Can you shed any light on that?
Well, we don't like to talk about our customers' payloads. That's up to them. So we respect the privacy of our customers. So I would direct your question to Robert Bigelow. One thing I should point out, though, is that I think we've got about 46 or so launches on our manifest, and not all of them are actually on the website. Almost all of them are, but not all. And 12 of those are for NASA, but the remainder are commercial. So sometimes people are under the impression that NASA is the vast majority of our business, but actually they're the biggest single customer, but they're about a quarter of our launches.
Given that you had the anomaly in the most recent Falcon 9 launch, and there's been a slip in the next space station resupply mission, how will that impact the number of flights you can get up during 2013?
Yeah, I don't think anything that's happened will affect the number of flights we go for next year. I think we'll probably do 4 flights, that's my best guess. 5 if we're lucky. And one of those flights will be the last of the Falcon version 1s, and then we expect to do at least 3 flights of the upgraded Falcon 9. And then we might do a 5th flight. We'll see, but we'll certainly have the rockets produced. I feel very comfortable about how the rocket production rate is ramping. So we'll have the rockets on the ground, and so it's just a question of if the satellites are ready or if there are any other constraints that or unexpected things we encounter. But we'll have the rockets manufactured.
I think at this point I'll ask one of the questions from the people on Twitter. This question is from Detlef Kreuzer. He says, what do you think is the next great challenge for rocket technology after reusability?
Well, I mean, it's a big one, reusability. Better reusability is, I mean, once we have reusability, I think that definitely improvements in reusability are going to be incredibly important. I mean, I think, I mean, that's really the fundamental one. So I wouldn't say that there's, I can't think of anything that's on par with that, sort of like warp drive. It would be very cool.
Okay. Maybe I'll link it to another question. Once you've cracked that problem, this question came from, what is it? Paolo Sergio Martins. You've done online banking with PayPal, you've done electric cars with Tesla, you've done private space flight with SpaceX. What are you going to do next?
Well, I think I've just focused on SpaceX and Tesla for a while. In fact, I'd like to just slightly decrease the amount of time that I work. I think I'll be able to do that when Tesla's cash flow positive, which hopefully is quite soon. And then I definitely do not want to run a third company. So I have some ideas, like the Hyperloop, which I think could be cooler than sort of just having another bullet train. And I hope I'll be able to publish something like that later this year, something on that later this year. I want to vet it with the team at SpaceX and Tesla and maybe a few other people, put it out there, and then ask people to kind of contribute ideas and see if there's some better way to deal with, to make it even better, like kind of like a wiki version of it or something. And then it can be there can be some collaborative standard design that people sort of collectively think is a good way to go, and then anyone who wants to build it can just build it. I think that'd be great. And I mean, I do think that there's potential to have a supersonic, vertical takeoff and landing electric jet. And I think that's where things will eventually end up, just a question of how long it takes to get there.
More questions from the floor?
Hi, Elon. Actually, I'm doing a PhD in aerospace at Bristol, and also a pseudo South African. My question is, in your opinion, honest opinion, with political inertia and consideration of governmental bureaucracy, who will be the first to put people on Mars? A single nation, a multinational hyper, a private company? Who do you think?
Well, I'm hopeful that the first human mission to Mars is actually some collaboration of private industry and government. But I think we also need to be prepared for the possibility that it has to be just commercial. So that might take longer because it would require marshalling more resources, or you have to get the money together to do it. But I want to prepare for a scenario where either path is possible. It basically needs to happen one way or another. That's the important thing. I'm not dogmatic as to whether how it occurs, just that it occurs.
There's a question in the back.
Really short from the Solar Space Center. Over the next decade, China is going to be a very large force, and a lot of technology and a lot of space endeavors will be coming from China. Being an American company, so being a commercial company, will you be taking a cooperative approach with China, working with their companies to get stuff into space, or will you be more competitive against China?
I think we'll probably be competitive. Collaboration is difficult, because China will have that. I'm not sure they want to collaborate. And sometimes competition is good. So my guess would be there's probably not collaboration, but hopefully friendly competition.
Sorry, Bill Carville, King's College London. Just wondering, how is SpaceX working or collaborating with to overcome the physiological challenges you're putting across that with the going to Mars and back? Sounds amazing, but how are we working towards that with SpaceX?
Sorry, what was the beginning?
The physiological challenges
Oh, okay.
going to Mars.
Sure. I think it won't be too bad. I mean, clearly we know we know that people can survive in deep space because you know, astronauts that went to the moon lived long lives and just none the worse. And we also know that people can live in 0G for long periods of time. I think the record is almost 2 years or something like that. And there are plenty of cases where it's 6 months to a year, which is the journey time to Mars. So you do need to exercise along the way and make sure you don't have muscle and bone atrophy. But I think it'll be okay. In terms of shielding against solar radiation, sort of a solar storm, I think sometimes that problem is stated as you need several meters of water, to shield yourself, and then somebody does a calculation for the volume of the sphere, and that ends up being some enormous quantity of water. But you don't need to have that. You can just have a column of water pointed at the sun, and make sure that you're mostly in front of that column, and you should be okay. So I think it'll be. I don't think it's a huge showstopper. It's certainly not a showstopper, and we'll figure out ways to make it better and better over time.
Sorry, not on headhunting, but is there like a research division of SpaceX?
There will be, but there isn't now, because we're just focused on the things that I was talking about, but there will be at some point, yeah.
Hello, Matthew Taylor from Holomatics. I wondered whether you were familiar with a British company called Reaction Engines.
Right.
Sabre engine, and what you thought about the technology, whether you thought it had a...
And this is sort of using everything first stage or
yes,
everything assisted.
Right.
Right.
Very much cooling.
When I looked at the numbers, it didn't seem to be compelling relative to simply having a slight increase in the size of the first stage. So if you're going to add a bunch of complexity, it needs to really pay off. At least the numbers I've seen, I have a hard time seeing how it does pay off. But I could be wrong about that. And if there is really a big advantage, then it would be worth investigating. But I would be sort of, it would have to be a big advantage because I'd be reluctant to add essentially some sort of jet engine on top of the rocket engine problem.
Hi, this is Nikhil Anand from Imperial College. I wanted to ask you, what is your opinion on horizontal air launches?
That's a tricky one. Well, I think what's important to bear in mind that the payload to orbit advantage from an air launch is negligible. This is perhaps not, I think this audience probably understands that, but most people don't. Because it seems like, well, you're high up there, and so surely that's good. And you could be going at, say, 0.8 or 0.7 Mach, and so you've got some speed and altitude. You can use a higher expansion ratio on the nozzle. Doesn't all that add up to a meaningful improvement in payload to orbit? The answer is no. It does not, unfortunately. It's quite a small improvement. So it's maybe a 5% improvement in payload to orbit, something like that. And then you've got this humongous plane that you've got to deal with. Which is just like having a stage. So if you say, well, from a SpaceX standpoint, would it make more sense to have a gigantic plane or increase the size of the first stage by 5%? I'd take option 2. And then once you get beyond a certain scale, you just you just can't make the plane big enough. You know, and when you drop the vehicle, when you drop the rocket, you have slight problems. You're not going in the right direction. And so if you see what, say, Orbital Sciences did with Pegasus, and have the delta wing to do the sort of turn maneuver, but then you got this big wing which has added a bunch of mass, and you're able to mostly, but not entirely, convert your horizontal velocity into vertical velocity, or mostly vertical velocity. And the net is really not, it's not great. And so Orbital, for example, would be an interesting example where the Pegasus, they started off with the Pegasus as an air-launched vehicle, and then subsequently did not do any air-launched vehicles.
John London, science communicator. Probably everyone here is fairly confident that the technology is there in the future to get people to Mars. But I'm interested in the financial aspects of this. I mean, what is the investor's pitch to say, I'm going to make money going to Mars? How do you make money doing that?
Well, I think that there is definitely there's some amount of money that will need to be spent establishing a base on Mars. It's basically getting the fundamentals in place. Call it sort of like the activation cost of a Mars base. And that was true also of the English colonies. You know, it really took a significant expense to kind of get things started. And you really didn't want to be part of Jamestown. You know, that was a rough one. So it took quite a bit of effort to get the basics established before before the subsequent economics made sense. So there is that investment, and you know, so one would need to gather the money to do that. But then once there's the regular flights, that's where I think it's important to get the cost down to the $500,000 range for somebody to move to Mars. Because then I think there would be enough people that would buy that, you know, to sell this stuff on Earth and move to Mars, to have it be a reasonable business case. Yeah, I mean, it doesn't need to be. There's 7 billion people on Earth. Probably reach about 8 billion in this century, and the world on the whole is getting richer. So, so I think even if 1 in 10,000 people decide to go, that would be plenty. Or even 1 in 100,000.
How many people do you expect to go on each journey to Mars?
Well, in the beginning, you'd go with a smaller number of people, and you'd have a higher proportion of cargo and emergency equipment and that kind of thing. Once you really got rolling, you'd increase the number of people on the flight, because you'd have supplies there. So you wouldn't need to worry about, you know, carrying with you all the supplies for the journey there, staying on the surface and coming back. So initially you start off with maybe a handful of people, less than 10, you know, just trying to give orders of magnitude here. But then you go to 100 or more in steady state down the road.
Question from the back.
Go flying.
David Top Flight Global. I was just asking about the MCT engine that you mooted in being about £1.5 million thrust. Are you planning to build a pretty big booster vehicle like SLS class?
MCT is not an engine. We're only doing one engine, one major engine, and that's the Raptor engine, which is the methane engine. We can talk more about the details of that next year, but we're not doing another engine.
And on the subject of methane, are you going to work with Russians at all?
No. We might hire a few Russians, but yeah.
Ryan Laird, Space Generation. I'm just asking, would you envisage yourself going to space or Mars?
I would like to go to Mars, yeah. I'd want to make sure that things are going well on Earth. You know, like basically, if I die, then I want to make sure that things keep going the way they should. as long as I felt confident with that, then I would go.
Alessandro Bonino, RAS Bristol. I think we got used to see first NASA leading the way in space in the 70s and 80s, and then now that the private sector is taking the seat, US companies are leading the way again. So what do you think is the situation in Europe, and what do you think are the main obstacles, and what would be your advice to improve this direction?
My advice with respect to, say, Ariane is that I think any variant of the Ariane 5 is not going to be competitive with Falcon. So the right move, I think, would be to rethink the architecture of Ariane 6, or I'm not sure if one wants to call it Ariane 6 or something else. But think very carefully about that architecture and make sure it has a chance of competing against Falcon. Otherwise, it's kind of a pointless exercise. I feel like I'm stating a super obvious thing.
I'm Saman from Solar Space Center, and just off the topic, what do you think about technology, far-fetched technology like space elevator and stuff? Do you see any opportunity or any point in that?
I'm not too sure about the space elevator. It sort of sounds intuitively appealing. I always sort of think of Charlie and the Chocolate Factory. That's very much a space elevator. The problem with space elevators, first of all, you need a lot of launches just to get the carbon nanotube rope up there in the first place. And then this thing would be anywhere from 40 to 60,000 miles long. That's long. And nobody's yet built a little footstool out of carbon nanotubes, as far as I'm aware of. So having something that's 40,000 miles long is a big leap. And then there are other issues. It ends up being this big sweeper going through Earth orbit, and any orbital debris is going to be really good at catching. And it's going to be very high impact. So, and then once you get to the end of the elevator, you've got to do something. You can't just be flung out into space. So you still need rockets. So really all the space elevator would be is potentially a means of reducing the cost of transporting propellant to orbit. But in that light, I would regard it as a long-term optimization, not anything worth working on right now.
Hello, Chris Bramley, Sky Night Magazine. I just wondering if you could tell us what stage SpaceX is at towards putting crew capability in the Dragon capsule.
So in terms of crew, we expect to be ready to, we expect to fly our first crewed mission in about 3 years. Technically, if someone were to stow aboard the cargo version of Dragon, they'd actually be fine. Hopefully. If it came back, they'd be fine. Because in the pressurized volume, we actually maintain sea level pressure, we remove humidity, we maintain the temperature very precisely, because we're required to transport experiments that have plants and mice and fish and that kind of thing to orbit and back. So you can certainly stow away and do it, but in order for it to be really safe enough, we want to establish a new standard of safety beyond the space shuttle and any stuff prior. So you really want to have a launch escape capability, and you want to have lots of flights under the belt and test it kind of without anyone on board before putting people on board. So the long lead for us is for Dragon version 2 is the testing of the launch escape system, and that's what drives the 3-year time frame.
As a young engineer, the work you've done is very inspiring. What was your largest inspiration?
Largest inspiration? I guess I read a lot of sci-fi when I was a kid, and I'm not sure. There's many forms of source of inspiration. I mean, I really like the Asimov books and the Heinlein books, and R.C. Clarke, obviously, and you know, movies. I like all the obvious stuff like Star Trek, Star Wars, Battlestar Galactica. From an inspiration standpoint, I guess I just want to, you know, having read all those books and seen the movies, and many other books and movies, you know, just the idea of having a future where that didn't come true just seemed terrible. You know? So that's why I started with this.
Why are you focusing on Mars rather than on the moon?
Well, we're happy to take people to the moon. If somebody wants to go to the moon, we'll definitely do it. But as far as a making life multi-planetary, you know, I think you sort of tautologically one must have a second planet. And the moon also is a sort of it's a small rock orbiting Earth, no atmosphere, 28-day period, very little water, lacking in a lot of the key elements that one needs for creating a civilization. It's analogous, I think, to the Arctic. The Arctic is close to Britain, but it kind of sucks over there. So, and so that's why America is not there. It's where it is. Even though it's a lot harder to cross the Atlantic than to. I mean, from Norway, you could practically road to the Arctic. In fact, I think they did. It's really because it's the place where one can establish a self-sustaining civilization and really grow it to something significant, really big. And in a worst-case scenario, if something were to happen to Earth, that you have a redundancy. Whereas I think that would be much harder to do on the moon. And plus, if something calamitous happened on Earth, the moon's very close, so it might affect the moon too.
The Gerard K. O'Neill idea was that he spoke of planetary chauvinism, I believe. You know, do you give any thought to building colonies as opposed to, you know, space colonies as opposed to building colonies on a planetary surface?
Well, the problem with space colonies, it's not that it can't be done, it's just, that's doing it the hard way. Because in order to create a substantial space colony, you have to transfer mass from a planet or from some, you know, an asteroid or something. You have to move mass from one place to another. So why move mass from one place to another instead of just going to where that mass is in the first place? You know, any sort of orbiting space colony is always, in order to expand, is always going to have to pull mass from somewhere. And why bother doing that? It just seems like a much harder thing to do than just go to the
Well, the argument there would be to use asteroidal material and put your colonies so that you haven't got the gravity well, which you're going to have with Mars or a planetary surface.
Yeah, but it would actually be harder to travel to the asteroid belt than it would be to travel to Mars. So if you're talking about people coming from Earth, it's going to be easier to go to Mars. And Mars having the atmosphere, you can use atmospheric braking as well. You just have an enormous number of resources on Mars. Mars is like, it's not perfect, but it's pretty good. It's got a 24.5-hour rotational period. It's got a CO2 atmosphere, which means that if you just had a transparent dome, pressurized dome and a pump, you could actually grow Earth plants in Martian soil. In fact, it's recently turned out that Martian soil is non-toxic, so you can actually grow Earth plants in Mars soil just by heating it up and pressurizing it with CO2. Simplifying. And, you know, you need a little fertilizer. Actually, but Mars has I think 2.7%, something like that, nitrogen in the atmosphere, which means you can synthesize fertilizer as well. So yeah, I think it's a pretty good option. That's the only option, I think.
Okay, at this point, I'll ask one final question from the Twitter feed. This question is from Chris Davies. If spaceflight becomes accessible to the general public, what will it mean to the idea of what it is to be a human?
I think we'll be making it more awesome to be a human. eventually spread out to the rest of the solar system and start sending ships to other star systems. And once we've got a planet and a large base on Mars and a lot of travel between the planets, that's going to create a great forcing function for the improvement of space transport technology. I think we'll see rapid improvement and all sorts of inventions that we just can't envision today.
We're going to try and finish the questions and answers by about 10 past, so we've got time for 2 or 3 more questions. So, and people who haven't asked them, can we prioritise people who haven't asked questions yet? There's a hand up over there.
Hello, Mohammed from MBDA. This is more of a commercial question. What kind of business model do you see operating within SpaceX in a few years' time when you have reusable vehicles? Do you plan on selling them as Boeing does to airliners, or do you plan on operating them?
Well, at least in the short to medium term, we would operate them, but I'm not averse to selling them and having others operate them. It does require some additional effort to be able to hand off something so that somebody else can use it. But I think long term it probably will be an airline type model, and short to medium term it will probably remain something similar to how it operates today.
Do you have any idea of market forecast and how many you think you'll be able to sell?
Market forecasts are always tricky. I mean, like if you ask someone at the dawn of air flight, what are your market forecasts? I mean, they're going to be wildly wrong. Probably on the low side. I mean, even probably the most optimistic people in the early days of aviation would seem like pessimists today.
So you've read Heinlein, if I might take a quote loosely out of context, it is if you're in orbit halfway to anywhere.
Well, it's not quite true, but it's close enough.
It's close enough.
You're not halfway to Alpha Centauri.
Yeah, as long as you stay in the plane in the ecliptic as well. Does SpaceX have any plans for, let's call them esoteric engines, things like NERVA upper stages or nuclear light bulbs? You dismissed the space elevator. I love it, but it's 50 years away.
Yeah.
Does SpaceX have any upper stages that are a little bit more interesting than just liquid fuel rockets?
Hey, I think liquid fuel rockets are pretty interesting. Throw me a bone. Yeah, I mean, I think there's for interplanetary transport, having high efficiency, high thrust ion drives, I think could be helpful. Yeah, so that's sort of, I think that's something you'd want to do anyway, because if you had a big spacecraft with a lot of excess power generation, might as well, strap an ion drive to that. Yeah, so there's this question of how efficiently can you convert power to thrust, and so that's one thing. And then potentially something like an electromagnetic sail would be cool. Yeah, I think that would be kind of neat. So on the nuclear side, I think that's tough. It's really tough taking up with a lot of nuclear fuel in a rocket. I mean, people have a hard time with establishing nuclear power stations. How'd you like one that's flying over your head and might crash? I mean, we all might think that's a good idea, but we're in the minority.
Hi, I'm Johannes from Imperial College, and this is more of a fun question. The video you showed on your plans and for reusability, it reminded me of a game I'm sure some of you have seen. It's called Kerbal Space Program. Have you heard of it?
No, what's it called?
Kerbal Space Program. I can write
Kerbal, okay.
Later. It's basically a very fun game, and it does exactly what the video does.
Oh, wow, okay, I didn't know that.
Yeah. Okay. Last question then. There was the first hand.
Hi, I'm Lisa Peacock from Astrodome. I understand that one of the reasons SpaceX
so fast and cheap at making rockets and spacecraft is that you have all of your design engineers and your manufacturing engineers located on the same site, and you design and make a lot of your stuff in-house.
Yeah.
I was wondering, is that the key, do you think, or a key? Do you think it is
Yeah, I think
going
it's
to
a key,
continue that
certainly.
way? And how much do you actually make in-house, and how much do you make? Is it what we should be looking to in Europe?
I do think vertical integration is sensible. And we're really, I mean, you just need to look at it and say, okay, if we made it ourselves, how much would it cost? And if somebody else made it, how much would it cost? And then go with the one that is more efficient. I mean, that's really how we operate. And that's resulted in, I don't know, 70+%, depending upon how you count it by mass, by cost, 70+% of the rocket is built from raw material at SpaceX. And, I mean, I actually would like to do less. No, it's not as though we want to do all this. If we could find more efficient suppliers, it would be great to offload some of that stuff.
Okay, I think at this point, Elon, I think we'll end the question and answers. I'll get everybody to thank you again for the talk and being so open with the answers to the questions. Very, very interesting.